Okay, so for this lesson we're going to be looking at the MBF3C version B, Unit 1, which is Geometry and Trigonometry. And we'll be looking at the first lesson. And if we scoot down here, we can see this is the first unit. 5 lessons here dealing with geometry and trigonometry. First 3 units are, we'll almost say, a little bit more drawing upon your elementary experience, and then when we get into lessons 4 and 5 of this unit, we get definitely into more grade 9 and 10 work in lesson 4, and then we get into some actual new grade 11 work in lesson 5. Okay. A little bit of introduction that's worth reading, and you can see it reiterates right there lessons 4 and 5 in the middle paragraph of the introduction. These are we get into more newer things. Certainly in lesson 4 you'd have a bit of exposure. Lesson 5 is going to be new. Okay. Recognizing geometric shapes and why we even bother to study some of these different things in math. It's about an appreciation of math around us. A lot of people like to argue that, when am I ever going to use this? Not going to use it. Well, you don't really know what life's going to throw at you, so it's kind of good to know a little bit about a bunch of different things. Okay, so here's the lesson 1 in the unit 1 applications, geometric shapes. Okay, again, worth reading over the introduction just to give you a little bit of context about what this is talking about. What you're going to learn: recognizing basic geometric shapes, why geometric shapes are chosen, 3-dimensional objects and representations. Okay. It's going to be helpful if you have at least a ruler with you. Protractor might be nice, but certainly not necessary. Definitely a half-decent ruler would be a big plus to have for working in this unit. Okay, part A, reviewing basic shapes. Okay, this is very basic. We're talking, low elementary school type things here. We got a circle, 2-dimensionally. We could even refer to that as a disc. Okay, a disc. Sorry, more of a 3-dimensional type of a thing. A disc. You could think of something like a frisbee or a very thin slice of something cylindrical. So when we talk about a disc, we're actually talking about something more 3-dimensional, because it's implying already that it has a thickness. Okay, rectangle and parallelogram, again, a couple of shapes that you should have exposure to already. Trapezoid, it is basically a rectangle where the 2 sides have been sort of bent in, I suppose, at different angles, you could say that, as opposed to a parallelogram. With a parallelogram, the 2 typically narrower sides of the rectangle are still parallel, but it's been like somebody pushed it over on a bit of an angle, whereas a trapezoid, the 2 sides of the rectangle have definitely been brought in at different angles. Okay, so 2 of the sides, typically the way we draw it, top and bottom, are still parallel, and the other 2 sides are just very clearly not parallel. Okay, all the regular shapes, things you've probably been introduced to as far back as kindergarten or grade 1, triangles, squares, pentagon, maybe hexagons and octagons were a little bit later on, but certainly shapes that you'd be familiar with. Things like hexagons, we see those even in different game boards use hexagons. If look at a soccer ball or some different balls, you can see that the tiles inside of those balls are made with hexagon shapes because of the way that they fit together. There's certainly different types of architecture that incorporate hexagons for building larger structures as well. Octagons, same thing. It's actually a combination of octagons and hexagons that we use to build circular structures. Famous octagon to be a stop sign. Okay. When we take those simple 2-dimensional shapes and we stretch them into 3 dimensions, then we get these nice prism type structures, these 3-dimensional solids. So here we see a rectangular prism, triangular prism, and a circular prism, or a cylinder we often call that. And you can see that the tops of those shapes are very familiar 2-dimensionals that have just been stretched into a 3rd dimension. Okay. We have other different types of cones and pyramids where it's not just simply one shape that's stretched into a uniform structure. An example of that, the first one is the cone. You can see it's a circle on the bottom, but instead of that circle being pulled all the way up to create a nice cylinder, the edges are actually brought to a point, and so we refer to that as a cone. Same thing with the square and triangular pyramids. Okay, spheres are just balls. All right, and it's just a circle that has been rotated and twisted through all three dimensions equally and uniformly, and so we take a circle and spin that all the way around in every dimension possible, and we end up with a sphere. Okay, so getting on to the first support questions, and again, these support questions, there's usually fairly decent solutions to these at the back of each of the booklets. They're worked out to a certain degree or not, but this is just a video to maybe help walk you through these. And we need to identify these shapes and which ones are two-dimensional, three-dimensional. First one, pretty straightforward, right? That's an octagon, typical stop sign type of a shape right there. B, that's a rectangular prism. C didn't specifically talk about that in the previous lesson here, but it's basically just a semicircle. Okay, it looks like it's pretty much a nice uniform circle that's been chopped in half. And then we have a triangular prism there for D. Okay, so again, hopefully that wasn't too challenging at all. Stuff that you've seen already in elementary school. Okay, here they're just trying to emphasize the idea that these are all different shapes that you would see in your everyday experiences out in society, where we use these different shapes for constructing architecture, toys, useful items that we use on a day-to-day basis. There's the ball example I was talking about. This one's using we have pentagons here, and hexagons fit together inside this particular soccer ball. You can see a lot of different triangles and rectangles, very common in a lot of different types of architecture. And it's asking you to identify some of those different shapes here, just taking a minute to do that. And of course it works all that out for you in the next part of the example. Okay. A little bit more discussion, probably worth going over there. There's the idea of a parallelogram just being a rectangle that's been sort of pushed in one quarter. Okay, and then back onto the next set of support questions in this lesson. So out of cost, structure, and aesthetics, what do you think is the most important factor to consider when designing the following things, and explain your choices? So a bridge, it wants you to consider the cost, the structure, and the aesthetics. I think if you had to put those in order for a bridge, you know, generally with most things that are funded by the public governments, cost is a big driving factor in there, but certainly structure, because these different types of projects would have to be designed to withstand a certain amount of capacity for the amount of weight that's going to be going across there. So certainly the structure is important, equally as important as the cost. And then aesthetics, if the architect who's going to design that, or the civil engineer that's going to design that, wants to be able to work in some aesthetics into the design as well, I would say that would be the least important of those three factors right there. A carton for shipping boxes of macaroni, well, that's interesting now, because you want to have the structure of that macaroni box being the most efficient it can be in terms of the amount of macaroni volume that it can contain, and the size of that box as a relation to its volume. So cost and structure, again, if the manufacturer can keep the cost of the container box to a minimum, and the structure as simple as possible, then that's good, because that's going to translate into more profit for the manufacturer of the macaroni. But now you have to consider some of the marketing here and the aesthetics of the box to ship that in to hopefully attract more customers to your box of macaroni as opposed to the next box of macaroni that's sitting on the shelf. So there's a lot of things there to take into consideration. A diamond necklace. This is interesting in part C, because a diamond necklace, this is really not something that anybody needs. This definitely falls into the want category here. And I think somebody who could afford a diamond necklace cost is probably not the most important thing when considering the design of a diamond necklace. I would say here that aesthetics is probably the most important. When you're designing jewelry, you're usually looking more for the aesthetic component of the jewelry first. It would also need to be structurally sound, because somebody's going to buy a diamond necklace. They don't want it to fall off their neck. It's going to be an expensive cost for them, and so I would think that cost is probably the least important of those things. Number 3, analyze design of the chair shown below in terms of its geometry. Okay, and in other words, indicate what 2- and 3-dimensional shapes are used, justify whether design is appropriate. I think if you look back there in the lesson, you can see that right there they're showing a semicircle on that chair. Probably not hard to imagine some other shapes that are in that chair as well. Fairly obvious what some of the other shapes would be. Okay, part C now, scale diagrams. Obviously, very few things can be drawn life-sized on a sheet of paper when we're talking about designs. Think of the designs of a house, or even something as simple as a garage. You're not going to design those to be life-size drawings of those particular structures. There's going to be a scaled down version that the people who are going to be building that structure will be able to refer to, that again the designers have made, be it an architect or an engineer, that have laid out these plans, and they will be designed to a very specific scale, so that the person building it can use that to build the actual real life size object. Okay, so this is going to be worth reading all of this. And that works in reverse as well. If we think of the electronics industry, things like microchips that drive everything that we have, your cell phone, calculator, computers, everything, those particular devices, the microchips, are so absolutely microscopically small that when those designs are originally laid out, they're laid out much larger, and then they are scaled down very small. So scaling up and scaling down is something that's very commonly used. Even going back to the jewelry example with the diamond, before diamonds are even cut from the rough stones that they're dug up from the mines, the layouts of those stones, a lot of time and energy with the jewelry designers go in to maximize the geometry of how that diamond is going to be cut, because of course they're going to, the larger the diamond that they can generate out of these raw diamond stones that come out of the ground, the higher the profits are going to be. The larger the diamond, the more money they can charge for it. Okay, and so they're talking here about an example of a bedroom. Bedroom is 6 meters by 4 meters in size, and there is a 2 meter by 2 meter king size bed against the middle of the shorter wall. Draw a scale diagram. Well, this is interesting because they're using metric dimensions here, which I suppose are okay. Unfortunately, in North America, we tend not to build very much in terms of metric dimensions. Most of our dimensions that we use, especially for residential building, are imperial units. Even though they have been translated into metric units, the reality is the majority of the building materials that we still use here in Canada and in North America as a whole are imperial based units. But anyway, for the sake of this exercise, we can see that the bed is 2 meters by 2 meters, and the room is 6 meters by 4 meters, and there's a drawing. Okay, and it wants you to try that out as well. Okay. With that 1 to 40 scale. So with the 1 to 40 scale, okay, the 1 to 40 scale is every unit that you see on the physical drawing in reality would be 40 times that when you actually measured it out in life size, so to speak. Okay, So that's what the 1 to 40. So 1 centimeter on the drawing would in reality translate to 40 centimeters in reality if we were measuring out on the actual floor. Okay. So on to the next set of support questions here. In this unit, diagram A below has been reduced to produce diagram B. So we can see it's sort of a shrinking down of diagram A to diagram B. It says determine the scale used to produce diagram B. So what you're going to have to do on this one here is you're going to have to pick one leg of this diagram A, or of this diagram A, and you're going to have to physically measure that. So if I just slide this over here, and I just do a quick sketch of diagram A, just the top part of it. Okay, so this will be diagram A, and then we have diagram B beside that, which is a scaled down version like that. Okay, and the question here is asking you to determine determine the scale used to produce diagram B. Okay, so we need to find out what the factor is, scaled down factor between A and B. So what you're going to have to do is you're going to have to measure the long side of diagram A. Okay, and on this one here, okay, we've now that's in inches. You're probably going to want to work in centimeters because that's probably what you're more used to. So if I make this just slightly longer, I'm not even sure what I'm doing here. In terms of the length, it's not just, you can see that I just sketched this out quickly. And this is just going to be an example. So this is 7 centimeters in length, okay, that's been drawn out. And then when I look at the other side, this is just about 2 centimeters in length. Okay, so we'll say that that's 2 centimeters. Let's give it a little bit of a stretch there. 7 and 2 like that. Okay. So the scale now is a ratio here. I could say just quite simply that the ratio between the two is 7 to 2, like that, because every 7 centimeters on my larger drawing is represented by 1 centimeter on the smaller drawing. Now generally with these scales, we like to have them in terms of one larger number to 1 to a unit. So basically what I need to do is I need to take this, and since 2 here is the smaller number, and I want to get this down to a 1 factor. Okay, this is a 1 factor. Like you can see in the example, it was 3 to 1. If I divide this side by 2, it's just a basic ratio. I have to divide the other side by 2 as well. And when I divide 7 by 2, I get 3.5. Okay, so I could write it as 3.5 or 3.5, whatever I want. So the scale factor here is 3.5 to 1. Okay, because again, we've got this down to a ratio of 1 instead of being 7 to 2 here. This isn't wrong. It's just that generally when we're talking about ratios and scale drawings, we like to have it as a particular number to 1. Okay. Now it wants you to draw an enlargement of diagram A using a scale of 3 to 1. So that's going to be going in the opposite direction now, where you're going to take a measurement of A, and you're probably going to take a good part of the piece of paper here and have to enlarge this to make a larger drawing. Okay, and since my diagram A happens to be 7 centimeters, my my enlargement, since it's going to be a 3 to 1 enlargement, means I'm going to have to increase this here by a value of 3. So for my enlargement, my 7 centimeters is going to increase by a factor of 3, which means in my enlarged scale diagram, my side that's 7 centimeters in my original diagram A is now going to get bumped up to 21 centimeters in my enlarged diagram. Okay, so I'm going to have to, now you won't be able to see this down here, but this isn't going to fit on this one piece of paper for my purposes, or for the purposes of this diagram, but just to quickly illustrate what you're facing, here is a 21 centimeter long side that I've had to draw on this piece of paper, and I'm going to have to draw another corresponding 21 centimeter side over here, which is really taking up this entire piece of paper here. Okay, to be able to blow up this magnified just top of that drawing. Okay, so I could call this my drawing C if I wanted to, and this is just the top of it here. So where this side was 7 centimeters in the original with a 3:1 magnification, my 7 centimeter side has now become 21 centimeters. Okay, so fairly straightforward, and you just have to complete that exercise. Okay. If we continue along here, Carpenter has given you a rough sketch of a room with the measurements and wants you to make a scale drawing using the scale of 1 to 50 now. All measurements are in meters, but you should work in centimeters. Again, we're talking about most things in a residential type of a room. We pretty quickly get up into the meter range, and we're going to be working with a lot more decimals than necessary if we keep working with meters. So it's probably easier to work in the centimeter range. And again, most tape measures or rulers that you would use are well graduated into the centimeter unit of measurement, so better to work in centimeters. So it says to convert the carpenter's measurements to centimeters, multiply each measurement by 100, because there is 100 centimeters in each meter, right? So 1 meter equals 100 centimeters, because that's what centi means, right? The prefix here, centi, refers to 100 or 100th. Okay, somehow we're talking about 100 when we use the prefix centi in front of meter. Okay. So you get this drawing here now, and this was just a rough sketch, so maybe he just went into the room and sketched out, just did a rough sketch of the room. And now what you need to do is redraw that with a scale of 50 to 1 with a reasonable amount of accuracy. Okay, and you may want to use a piece of graph paper for this. Okay, that might help you out. You don't have to. If you're careful on a regular piece of paper or just regular line paper, you can certainly do that. Okay, and a 50 to 1 ratio here. Okay, so if we look at that first side, slide this over here a little bit, and I'm just going to draw a portion of that drawing like that right there, and we have 4 meters here. We have a window located in this space right here, and he's indicated that the window is 2 meters. There's a space from the wall, 1.5 meters. This is 4 meters, the length of that wall, and the length of this wall is 6.5 meters over. Okay. And we need to make a 50 to 1 ratio, I believe. Let me go back here. Yeah, so convert everything to centimeters and use a scale of, 50 to 1. Or 1 to 50. Okay, so first thing we need to do is convert the 4 meters into centimeters. So this becomes 400. That's 400 centimeters. 1.5 meters is 150 centimeters. 2 becomes 200 centimeters. and the 6.5 on the bottom, that becomes 650 centimeters across the bottom, just to go through a few of these drawings here. Okay, and now we need to divide all of these by 50 to get them into our scale length that we're going to use for our drawing. So when we take the 400 and we divide that by 50, okay, when I divide that by 50 for my scale, this is going to be an 8 centimeter length right here when I draw it on my actual drawing, okay, on my scale drawing. On the bottom, the one that's 650 centimeters, I take the 650 and I divide that by 50, and this is going to become 13 centimeters on my drawing. Okay, if I take 200 and divide that by 50, I'm sure some of you can just do that in your head, that's going to be 4, and this is going to be 3 centimeters because I'm dividing each of these real life measurements by 50 to get this 1 to 50 ratio here, or 50 to 1 ratio on the drawings. Okay, so then it's just a matter of redrawing to scale the length of, and I'm going to switch to another piece of paper here. I'll move this over so I can see the piece of paper a little bit better. Okay, now I can see it off to the side over here, but this length of this wall is going to be 8 centimeters. You can see right here. Okay, so that's 8 centimeters. And I need to go 3 centimeters in across the top here. Okay, and then I'm going to have a 4 centimeter window, which 3 plus 4 takes me to 7, and that's going to continue on. And then across here, I need to have a 13 centimeter wall along here. So I draw this along here to 13 at this point. Now, you're probably going to have to turn your page sideways here. It takes a little bit of planning to figure this out. But this is 8 centimeters, so this is a 1 to 50 scale drawing, okay? And as we saw in our rough calculations, this length right here is actually a real 3 centimeters that I just drew on the drawing. This is a real 4 centimeters that I just drew on the drawing. This is 8 centimeters, and this is 13 centimeters. Okay, I haven't done the whole drawing. But in reality, what do those measurements represent? Well, because it's 50 to 1, a person would pick up this drawing here and they could measure that out and realize that whatever they measured here, they're going to have to multiply that value times 50 to get the real construction size. So when I multiply 3 times 50, in reality, that length right there from the wall to the edge of the window is going to be 150 centimeters. And then the size of the window itself, when I measure that out, I get 4 centimeters on the drawing, but when I multiply it times 50, I realize that that window opening is actually 200 centimeters to there. And same thing about the length of this wall right here, the 8 centimeter scale, multiply that times 50, I realize that that's actually a 400 centimeter wall. Okay, and you would just keep doing this to complete that entire diagram. Okay, so everything is either divided up by 50 or divided down by 50. Okay, and probably a good idea to turn your page sideways so that you'll be able to do this entire drawing and get it all done. Again, you know, a piece of graph paper might be nice there, but certainly not necessary. Just be careful and draw it out nice and square with your ruler. Okay, so now moving along. Orthographic drawings of 3-dimensional objects. Wow, those are that's a big word right there. Orthographic. In some types of drawing and manufacturing and engineering and technology and drafting and design, you have real 3-dimensional objects, but you want to be able to draw them out on paper, especially 3-dimensional objects that aren't nice and uniform. Hopefully you've played with some different little blocks and things like that throughout elementary school, or even like Lego blocks. And when you look at one face of a particular side of that three-dimensional object. It's not a completely uniform object, like say a regular type of a box, like maybe a Kleenex box, which is a nice rectangular solid for the most part. We might get something that looks like this right here. And again, we do these orthographic drawings of these three-dimensional type shapes. Okay? So to get these orthographic drawings, and ortho, think of the prefix graphic. Okay, so graphic is just drawing, but ortho, some place that you might have come across the prefix ortho before is orthodontics. If you've ever had braces or know somebody that has braces, orthodontics. People go and get braces. Why do they get braces? They get them on their teeth to straighten them out, to make them nice and square and parallel and look all pretty. So ortho somehow refers to the idea of straightening something or being very straight. So when we think of this type of a drawing right here, this three-dimensional drawing, we're not so much looking at it straight on. We're looking at it sort of in a twisted view, so that we can get a good representation of as many sides as possible and get an idea of the three-dimensional aspect of this drawing here. But when we draw an orthographic drawing, we do quite the opposite. What we do is we now take that particular shape and we look at it very specifically from three different dimensions. Now what you can see here is that we're looking face on here, and you can see that little dip in the middle there, which represents that little dip. This is kind of like a seat, almost like a throne type of a design, a very large throne type of a design. If we look at that, imagine looking straight on from the front. You can see where it's labeled front. And if we looked perfectly at the front of that shape, this is exactly what we would see here. We wouldn't see it in its three dimensions. We would only see just that one face dimension, and this is what it would look like. Okay, and if we drew it out nicely, this is what we would see when it was properly drawn out, and we have a scale of 1 to 5. So again, remember, every measurement on this physical drawing is really 1/5 of what the actual drawing should be. Okay. Now imagine rotating this and we look down upon it from the top. We would see something that looks like this. So again, a straight on view from the top. So that orthographic idea, we're looking straight on, the ortho prefix. And this is looking straight on from the front, or sorry, from the top, looking down. We can see the seat indentation in the middle there and the higher back at the top. And then finally, if we looked at it directly on from the side, this is all that we would see from the side. We don't see that little dipped recess in the middle where where that center channel is, or if you want to think of it like a seat in the middle or a seat space in the middle. That little channel is not visible when we look at it straight on from the side. We see the raised back, and then we see just the plain side there. Okay. But the other thing is that when we do an orthographic drawing, we draw it as if it was a transparent material. So instead of it being a solid block of wood or a solid block of metal or plastic or whatever it happens to be, we imagine this being a nice clear piece of material that we can look through. And when we look through that, when we represent it in an orthographic drawing, lines that we would see inside the material, you can see here, have now just been drawn and indicated with a dotted line. So when we put all three of those drawings together, which typically we see in an orthographic drawing, here's what you're going to see. And you would label all the side views. If we have the front, the side, and the top view. And it's only from the side view that we need to include that extra little dotted line, because we wouldn't be able to see a part of the facet of that shape there. So we move on to the next support question here, and it wants you now to create an orthographic drawing of this particular shape here, using a 1 to 10 scale ratio of what is given to you in these drawings here. Okay, so a 1 to 10 scale, which means we're going to have to take every one of these drawings and divide that number by 10, and this thing is really not being nice to me at the moment. Okay, there's what I want. Okay, then we need to redraw that. 1 to 10 scale. Okay, so maybe we'll just do a quick little sketch of this first, and draw the numbers before we get into the actual scale drawing. So I'm just going to do a quick little sketch here, just so I've got something to work with. Okay, this doesn't have to be too exact, too fancy. This is just going to be my rough work first, so that I can figure out all of the dimensions that I need. Okay, and it's going to be a 10 to 1 scale down. So on this back edge over here, where it shows in the original drawing that that's 30 centimeters, because this is a 1 to 10 scale down, this is now actually just going to be 3 centimeters across here in my scaled down orthographic drawing. And this is pretty simple because we're dividing everything by 4. That makes this a 4 centimeter high piece right here. Across the back right here, that's going to be 10. It's going to be 8 centimeters across the face here, which means I can assume that this is square. That's going to be 8 centimeters. And I have no reason not to assume that this whole thing is nice and square. So that's going to be 8 centimeters across there, 8 centimeters across there. And the height across here, this is going to be 6 centimeters in my scale drawing. This little stretch right here is going to be 2 centimeters. Okay, that's going to be 2 centimeters across there as well. All right, and knowing that the whole stretch across the face is 8 centimeters, and again, no reason to assume why this isn't nice and square across here. If it's 8 across, that's 2, that's 2, total of 4 means that this unlabeled stretch right here of this line needs to be 4 centimeters right there. Okay. Now, one thing that it doesn't have labeled on the drawing, but it does describe below, is the tunnel is 20 centimeters high and goes all the way through. Okay, so that means that this height in here, if it's 20 centimeters high, then in my scale, that needs to be 2 centimeters high as well. So that length right there, this length and that length, all of those lengths are going to be the same, and we can just mark those with a single line like that. Okay, so I've got my little rough sketch that's done right there, and so what I need to do now is create an orthographic drawing so I can label my front, my side. Okay, so I can label my front. Let's call this my front view. Okay, that'll be my front view looking right on in this direction. This will be my side view looking in that direction, looking straight at the block in that direction. Okay, my front view is looking straight on in this direction here, and then my top view would be looking down in that direction right there. And so that's how I'm going to create all 3 of my orthographic faces. Okay, so I'm just going to put this off to the side, and I'll use that to start creating my orthographic projections here. Okay, and just to right here. Okay, so again, we've got a front, a side, and a top view that we need to replicate for this shape right here. Okay, and again, it says the tunnel goes all the way through. Okay. A little bit. Refocus. Good. Okay, so starting with my front projection, I need to be a total of 6 and 4 centimeters high. So it's going to be a total of 10 centimeters because I have 6 on the front face and then an additional 4. So my whole front face is going to be 10 centimeters total, okay, because I have 6 centimeters from the bottom, and I have an additional 4 centimeters at the back, and so that's going to be my entire front projection. Okay, and then my total width needs to be 8 centimeters wide. Okay. But I got to be careful here because there's that little channel. So I need 2 centimeters for the first chunk, and then plus 4. So 1, 2, 3, 4 takes me to 6. And then there's my last 2 centimeter leg right there, which takes me between 6 and 8, like that. Okay. And then on the other side, I'm going to go back up the full 10 centimeters. Like that. I'm just going to mark the 4 centimeter point right here. Okay. And there's the top. There's the back edge, or kind of like the back seat of this thing. Okay, and how high up do I need to be here? Well, it said it was 20 centimeters in reality, which means that's scaled to 2 centimeters for this projection, or for this view, or scale, whatever you want to call it. Okay, like this and this, and then we have our 4 centimeters across there, like that. Okay, so there is our front. There's our front projection, our front view of this orthographic drawing of that shape. Okay. Now, if I do the side projection down below this here, curve up the paper a little bit. Now the total height of this is still the same. It's still 10 centimeters high. That's the overall height of the shape across the back. So I need another 10 centimeter height here. Okay, you might need to do this on 2 pieces of paper. The total length of this shape, if we go back here to our drawing. So again, we're using the 6 and the 4 right there to get the total height of 10 centimeters right there. Okay, across the whole back. But the total length of this is the 10 and the 3 centimeters right there, so I need 13 centimeters across the back. Okay, so I could have written that in on this drawing as well. I have a total depth of 13 centimeters here. And there's my total height of 10 centimeters. For this drawing, like that. Okay, because these 2 values are going to come in handy for drawing my my side projection. Now that could be the side projection, or I could take it exactly from the other side. It doesn't matter. I'm actually taking this from the perspective of the other side. So I've gone 10 centimeters high here, and now I need to go 13 centimeters across the base. Like this. And I only need to come up 6 centimeters here. Okay, because if we look again back at this drawing here, I'm actually taking the mirror image of this side here, or I'm coming at it from the back side over on this other side. So I've just rotated this. So there's my 6 centimeter height, and I got to go back 10 and up 4 and meet back there again. Okay, so the stretch across the top here is 3 centimeters. I drop 4 centimeters. When I drop that 4 centimeters, that puts me now in height with the other end, and there's 10 centimeters remaining here. Stretch across there, and now there is my side projection. But of course I did it in reverse here. I'm imagining myself coming at the back side. Actually, I've rotated it from the back side. So 13 and 10 across the back like that. Okay, so I would label this now as my side projection. Okay. But I'm not done here. I'm not done. Okay, because like I said, if there's any part of this drawing, imagine this as being sort of a clear material, a clear plastic or something like that, that is representing this shape. There's this channel here that runs through the bottom part of this. And I know that the height here is going to be 2 centimeters high, but it runs through the entire depth of this whole shape here. So what I need to do is just make a little mark here at 2 centimeters and make a little mark down here at 2 centimeters. Okay. And then I need to just draw in a little dotted line across that whole stretch, because that channel goes all the way through the back or the bottom of this shape, just to represent that if this was a clear see-through piece of plastic, I would see this little channel in behind here, but I use a dashed line because that's not a surface line. That's going to be a surface edge inside the drawing. So that represents this channel. Looking at this shape from the side, if I was looking at it from the side, I would see this channel space going all the way through that shape. Okay. And finally now I can do a top projection, and the top projection of this is going to be 8 centimeters wide, which I have just enough room for still on this drawing here. So it's going to be 8 centimeters on this piece of paper. I have 8 by 13. I'm going to start with my 13 first. That's the total length of this. There's my 13. And it needs to be 8 centimeters wide. Come across here to 8. And over here I go across to 8. Join up these two sides. This is my top projection, looking down perfectly from the top. Okay, so this shape has a footprint of 8 by 13, so this is my top-down view. And what would I see when I look down perfectly from the top? Well, I know that from 3 centimeters in on the top, I would see a little bit of, or I would see a straight line right across the top portion of this drawing here, because this straight line represents this line right here that I just drew, is now representing this edge that I would see right here if I was looking straight down from the top of this drawing. Okay? Straight down from the top. So that is this edge right here. If I'm looking straight down from the top view, looking down, that 8 by 3 centimeter surface right here that I would see would be cut right here before I saw the remaining 10, okay, 10 by 8 centimeter rectangle, which would be the other part of the face, and that's right here. Okay, so this is the 8 by 3 raised surface I would see, and this here now is the 8 by 10 main big face, which is this big face right here that I would be seeing if I was looking straight down from the top. Okay, but again, keeping in mind that this is some type of a clear crystal or clear plastic type of a material, I would also see this channel down through the bottom, and the channel goes all the way through the bottom. It's 2 centimeters in, okay, on the drawing here, and it doesn't matter where I start on the ruler here, it just needs to be 2 centimeters, so I'm just going like this right here, and then over here I'm going to go 2 centimeters, and at the other end I'm going to go 2 centimeters, and another 2 centimeters in from there. Okay, and this is going to be the channel indicated by little dashes that runs through the entire shape. I think I made a little goof here. There's 2. Aha, I did, and there's 2. I wasn't very careful there. There, like that. Sorry about that. Little goof right there. There's the channel that goes all the way through the bottom. Okay, so there is the orthographic projection of this three-dimensional shape, top, side, and front. Okay. To scale, 10:1. All right, so that's the end of the lesson. Now you're on to key questions, and what you need to do is make sure you start your key questions on a fresh piece of paper that you can hand in. And what you see here is another shape. Looks like a big squared off arch type structure. Gives you a lot of dimensions that you need. First part, name two-dimensional shapes that appear in the drawing. Pick two standard two-dimensional shapes. Identify those, pretty straightforward. Then it wants you to create an orthographic drawing using now a scale ratio of 1 to 8. So we did 1 to 10. This example wants you to use 1 to 8, which means you're going to have to take every one of those measurements, every one of the measurements that are on here, and divide them by 8, and then do a scale drawing based on that. Now, unfortunately, you're not going to have whole numbers of centimeters to work with. They will be decimal numbers. Not a problem. You can work with decimals on with your ruler. If we just take an example, the first one's going to be 10. If you divide 10 by 8, you're unfortunately going to end up with 1.25 centimeters. Okay, when we divide that bottom, the bottom stretch, but that's okay. Just do as close as you can with 1.25 centimeters on your drawing, and draw it as best as you can. Okay, it'll be just between the 0.2 and 0.3 on your ruler. Okay, so 1 to 8, and you can see here how that's going to be graded, and that will be it for the first lesson.